So here the optimization is, the first part of the lecture, we will do the optimization with respect to the sizes, keeping in mind for a circuit which has multiple branches. And later on, we will, introduce into the number of stages. All right. So it's an empty slide here. That means that I need to draw something. So let me create a single branch circuit and a single path circuit. So let's say that the initial I have one gate. It could be an inverter or an AND gate or a NOR gate or any other gates. And then we have one more gates here, and then we have one more gates here, and then finally we have some kind of a load here. All right. And so this is the input. So what we are saying is we wanted to find out, we were using the linear delay model, whether we can estimate the propagation delay from this to this particular point. So I'll call this point as a Y point, and then this particular point as an input point. Right. So to make it simpler, we have used a linear delay model, linear delay method. And we identified the P1 value, the G1 value, the H1 values. And similarly for the next stage, so this is the first stage, this is the second stage, and this is the third stage. The third stage is loaded with some external capacitance, or it could be considered as, a load coming from the another part of the circuit. And then similarly, the second stage, we will have the normalized parasitic, the logical effort, and then the electrical effort. And then similarly, P3, G3, and H3. So the linear delay model, the method says that the overall delay for the normalized delay is nothing but the summation of this Pi plus Gi into Hi. Right, where I is, for this particular case, it is 1 to n, where n is nothing but the 3 stages. All right. And now based on this particular delay, if suppose we have some kind of a constant value here, let's say we assume, we have some given gate size as 10, but the second and then the third stage is unknown. We should be able to find out what is the X value here, what is the Y value here, so as to attain the minimum delay. Right. So if I want to find out the minimum delay, we know that there are 3 stages. So one is this stage, the another one is this one, the another one is this one. So there are 3 stages. We will find out what is the overall path effort for this particular path, what is the overall effort, so that we can calculate it using Gi, Hi, and then the product of all the 3 stages. Based on that, we should be able to find out the best individual stage effort, so that we will get the minimum delay, which turns out to be nothing but f raised to 1 by n. So 1 by nth root of the path effort should give me the individual stage effort being the best, so that we will get the minimum delay. And then if we can calculate this one, then the minimum delay will be nothing but so the minimum delay will be nothing but the summation of all the parasitics for whatever the number of stages. Here it is 3 stages, and then plus the number of stages and individual stage effort. Individual stage effort will be f raised to 1 by n. So the 1 by nth root of f. All right. Hope this is something you have understood up till this particular point of time. Moving forward, let's say I have another circuit here. So I have the first stage here, and then the second stage, and then the third stage. And here it is slightly different in the sense that the first stage we see a 2-input NAND gate. The second stage, there are 3 branches. So the first stage output gets branched into 3 times. Okay. And then the second stage, in the second stage, we choose one of the 3-input NAND gates. So in the second stage, there are 3 such 3-input NAND gates, and one of them is connected to the first stage output. In fact, all the 3 3-input NAND gates are connected to the first stage output. But here I have made a arrow direction saying that this is the path we are interested in. So I'm going to consider this particular 3 input NAND gate, and output of this is going to the two such 2 input NOR gates. So the second stage sizes, and all of them, whatever gates we have here in the second stage, 3 input NAND gate, all of them have a size of X. And in the third stage, all the all the NOR gate, 2 input NOR gates have a size of Y. And the output is connected to some external capacitance, which is normalized to 45 into C. So that means that 45 times the unit NMOS transistor capacitance is what is the effective load which is seen at the output B here. The dotted arrows implies that we are interested to find out the propagation delay starting from the point A to the point B. Right, so we are not interested in any other paths, right? Any other paths mean from point A to somewhere here, this particular path, we don't know what exists after this. So we are not interested in that. We are not interested in this, the second output of the second 3 input NAND gate. What we are interested in is this particular path where in the first stage is the 2 input NAND gate, the second stage it is the third, the third out of the 3 such NAND gates, the third one, 3 input NAND gate, and an output of that which will go to the first 2 input NOR gate, and then that gets, goes to the 45C external load capacitance. All right. So it is slightly different in the sense that there is a branching at the output. There is a branching at the output of the first stage. There is a branching at the output of the second stage here. All right. So let me try to, if we are using the linear delay model, let's try to identify what are the individual P, G, and H values. So the individual P values is nothing but the normalized parasitics for the 2 input NAND gate or the 3 input NAND gates or the N input NAND gate is nothing but the number of inputs. So P1 will be 2 here for the first stage. For the second stage, P2 will be 3 here. And I have written P2 is equal to 3 here, which means that I'm considering this particular individual 3 input NAND gate. So I really don't care about, this particular one or this particular one, right? Although this will be included in some form, but, for finding out the G and P values, I don't really, it doesn't really matter because this is the 3 input NAND gate, which is going to drive the parasitics, which is going to drive the current to charge the capacitance at this particular node. Anyway, so P2 is equal to 3 here, and then we are interested in this particular 2 input NOR gate, so P3 will be 2 here. Okay. Logical effort for a 2 input NAND gate is nothing but 4 by 3. For a 3 input NAND gate, it is 5 by 3, and for a 2 input NOR gate, it is 5 by 3. Okay, so that is what is estimated here. Electrical effort, now we have to account for the 3 branching, right? So the electrical effort here, H1 in this for this particular stage, the output is getting a branch to 3 such 3 input NAND gates. That means if I find out the input capacitance at this particular node, the output of the first stage, the input capacitance that is coming from this particular branched 3 input NAND gate, from this particular branched 3 input NAND gate, and then from this particular 3 input NAND gates, overall I see 3x into the capacitance C. The input capacitance for this particular first stage 2 input NAND gate, if I consider the input capacitance here, it will be nothing but 8 into C. So my electrical effort or the fan out in this case will be nothing but 3x divided by 8 or whatever, 3xc divided by 8c, the c and c gets cancelled, and then finally we have the electrical effort or the fan out as 3x divided by 8. Right, hope this is clear. For the second stage, there are 2 branches. So the the overall capacitance that is seen, input capacitance coming from the third stage at the output of the second stage will be nothing but 2y into C. So the overall electrical effort or the fan out is nothing but 2yc divided by the input capacitance here. It will be nothing but x into C. So it will be nothing but 2yc divided by x into c. So we'll get 2y by x. All right. The electrical effort for the third stage will be nothing but 45C divided by Y. The input capacitance here for this particular input I'm talking about is nothing but YC. So this 45 divided by Y will be the electrical effort for the third stage. Right. Hope this is clear. Moving forward, so now I have a G value, P value and H value. So the overall delay, normalized delay will be nothing but the summation of the summation of Pi plus Gi Hi. Right. So that will be the overall delay. So that is something I might have written somewhere. If not, I will write it down here. So the overall delay here, the normalized delay, I'm going to write it down as the summation Pi and then Gi Hi. For estimating the minimum delay here, what we had identified is if I can find out a value of the product of Gi Hi. Right, so if I don't have the variables x and y, that is something we need to calculate so that we'll get the minimum delay. But if I somehow find out the product of Gi Hi, which is nothing but the path effort here, f value, so and then the product of Gi Hi, right, without having any variables x or y. So if I can find out that value, which turns out to be 125 here, right, so if I do the calculation, 4 by 3, 3x by 8, 5 by 3, 2y by x, and 5 by 3, 45 by y, if all the x's and y's gets cancelled, and then finally we will be having 125 value. The individual stage efforts, which will be, f raised to 1 by n, because 1 by nth root of the path effort. In this particular scenario, we have only 3 stages. So I'll do f raised to 1 by 3, which will be turning out to be 5. So that will be, we are estimating the individual stage efforts for the minimum delay. Right, so if I have the individual stage efforts, the best stage efforts for the minimum delay, I can now find out what are the variables x and y. So what are the gate sizes x and y, the optimum x and y values, so that we will get the minimum delay. So G1 H1 will be nothing but 5 will be equal to G2 H2 will be equal to G3 H3. What it means is all the individual stage efforts will be equal to the value 5. Right, so in that way, if I calculate this particular value, I should be able to find out what is y. Y turns out to be 15. And similarly, once I have the y value, I should be able to find out what is the x value. X turns out to be 10. So a y of 15 and an x of 10 in the circuit, in that particular 3-stage circuit, we will notice that that is going to achieve the minimum delay. And what is the minimum delay? We can find out using this particular formula expression, which is nothing but summation of Pi plus the number of stages multiplied by f raised to 1 by n, where n is equal to 3 here, so it will be 3 multiplied by 5, and then the summation of all the parasitics, which will be 2 plus 3 plus 2, which will be nothing but 22. So the lowest delay, the minimum delay we have calculated is 22, and this doesn't need the values of x and y, right? So we actually need what is the, we actually need the path effort, which is the f here. We actually need this particular value. If we know this particular value without the variables x and y, then we should be able to estimate the minimum delay. Right, so for the minimum delay calculations, if I know the input stage, what is the gate size, and then the output load capacitance, I should be able to find out the minimum delay without even calculating the variables x and y values. Right, so the x and y values we can estimate it and turns out to be 15 and 10 for achieving the minimum delay. So hope this is clear. If I know the values of x and y, x turns out to be 10, y turns out to be 15, and then the first stage is nothing but 8. So in that case, if the first stage is 8, what should be its transistor widths? So for a 2-input NAND gate, we know that the size of the PMOS and NMOS should be nothing but 2:2. So the gate size of 8, we will divide it equally into 2 parts, make it 4 and 4. 4 will go to the PMOS side and then 4 will go to the NMOS side. and both the inputs for this particular gate are symmetric. So that means that both the inputs are seeing the same capacitance. So both the transistors on the PMOS and both the transistors on the NMOS will see the same width of 4. For a 3-input NAND gate, the X value turns out to be 10. And remember, for a 3-input NAND gate, we have the size of 2:3. On the PMOS side, we have the size of 2 for a 3-input NAND gate. And on the NMOS side, we have the size of 3. Right? So what we will do is, whatever is the X value we have attained or we have achieved, we will divide it into 5 parts. 3 parts of that will go to the 3 of that parts. So 3 by 5 of the X value will go into the NMOS side, and 2 by 5 of the X value will go into the PMOS side. Right? So we will get 4 and 6 on the PMOS and NMOS respectively. If we have the value of Y as 15 for a 2-input NOR gate, remember that for a 2-input NOR gate, I should have 4:1 ratio. So the 4 being for the PMOS and 1 being for the NMOS. So I'll make it into 5 parts. So 4 by 5 multiplied by whatever is the Y value should be given to the PMOS side, which turns out to be 12, and 1 by 5 of the Y value will go towards the NMOS, which turns out to be 3. All right, hope this is clear. Moving forward, just for the curiosity, if my Y value is 15 and X is 10, we are saying that this is the optimum value. So this is the optimum value. That means that my delay is minimum. Right, the optimum value giving optimum value of Y and X is giving me the minimum delay. What if my Y value is reduced to 10? Let's pick a Y value, and just for a simpler calculation, I'm just picking a value of 10. One can pick any value like Y is equal to 12 or Y is equal to 20 or whatever. Right, just for a simple calculation, I've just reduced the value of 10. X, I have written it as 10. So now for Y is equal to 10 and X is equal to 10, what is the delay? With our claim, we are saying that Y is equal to 15 and X is equal to 10 is going to achieve the minimum delay. Right? So just to verify that our claim of optimum gate sizes is going to give me a minimum delay, I'm trying to verify it using a different Y values, using a different gate sizes. So what happens? So if I have a different gate sizes, let's try to calculate the delay from our expression of Pi and then the Gi Hi. So the normalized parasitic values doesn't change with respect to the gate sizes, so it will remain the same. The first one is the 2-input NAND gate, the second one is a 3-input NAND gate, and then the last one is nothing but the 2-input NOR gate. So I will have the normalized parasitic as 2 plus 3 plus 2, which is nothing but 7. In fact, the 7 value will remain constant, even if I change for a different X or a different Y values. The summation of Gi Hi will now change. So the summation, the very first stage, the very first stage is nothing but 4 by 3 is the logical effort of the 2-input NAND gate. That is the first stage. 3 branches, so 3 into X divided by 8. 8 is its the gate size that has been given, plus 5 by 3 being the second stage 3-input NAND gate. So 5 by 3. 2Y by X because it sees 2 branching. Each of the branch has gate capacitance or the gate size of Y. So 2Y divided by X plus 5 by 3. This is the 2-input NOR gate multiplied by the load capacitance of 45 divided by its input capacitance of Y, or input gate sizes as Y. What we have done is, we have taken a Y is equal to 10 with respect to Y is equal to 15. So I have calculated the delay, I have expressed the delay using this delay function, using this particular delay function in terms of X and Y. So I plugged in the value of X and Y, and then try to evaluate the expression. So in this particular, X is equal to 10 and Y is equal to 10. So Y is equal to 10. So I put in here X is equal to 10. and then y is equal to 10 here and x is equal to 10 here. So this is what I'll get. And in this particular expression, I have put x is equal to 10 and y is equal to 15, which we are claiming it is the optimum size giving the minimum delay. So I've rewritten that particular expression, but it's the same expression here, but the values of x is 10 and y is equal to 15. And this particular is nothing but the same expression here by substituting the value of x is equal to 10 and y is equal to 10. If I do this value of, if I subtract this particular, estimated or calculated delay value for x is equal to 10 and y is equal to 10, and delay of x is equal to 10 and y is equal to 15, if I do the difference here, turns out to be positive, right? So the difference is positive. What it means is x is equal to 10 and y is equal to 10 size, the gate sizes are giving me a delay more than the size that we had got the delay of for x is equal to 10 and y is equal to 15, right? So y is equal to 15 and x is equal to 10, which we were claiming that is an optimum size, which we were claiming that is the minimum delay, turns out to be true if I use a different gate size. If I use y is equal to 10, it turns out to be giving a slightly more delay. Right? Hope you have understood this. What if I use a y is equal to 20 value? So in the last case, we had taken y is equal to 10. That is the first case. The second case, I'm going to take a higher value of y, keeping the x as same as 10. It turns out that even if I have a y is equal to 20 here, it is a positive difference. So that means the y is equal to 20 and x is equal to 10 is going to give me a delay which is more than y is equal to 15 and x is equal to 10. Right? So in that case, it is positive, and thereby my delay is optimum or minimum for x is equal to 10 and y is equal to 15. For any other values of x or any other values of y, it turns out that the delay is more. All right. So that's what we have tried to verify it. So we had started that for if the individual stages sees the same effort delay, then we are going to get the minimum delay, the minimum summation of all the stage efforts. And that is going to give me or lead to the minimum delay. Here, by taking a different sizes, we have identified that if I use a different size than that of whatever we have calculated for the optimum sizes, then we are going to get a delay which is more than what we should obtain. Right? So for summarizing this, for a different y, my delay is actually more than what we achieve for an optimum size of x is equal to 10 and y is equal to 15. There's a small note here saying that if the input gate of 8 changes or the load of 45C changes, then I have to reevaluate the x and y value. Right? So I have to reevaluate the optimum x and y value. So if I have the 8 value change, the input gate side, the input to 2 input NAND gate, which is now having a gate size of 8, if it is changed to some other value, and then the load capacitance of 45C, that is going to be different now, then my x and y value, which was set as 10 and 15, that has to be different to give us the new minimum delay. Right? Because if 45 and 8 changes, the f value is going to change, and f raised to 1 by n is going to change, which is going to give me the individual stage efforts. This individual stage efforts is going to have a different GI, HI. So my x value and y value, which defines the HI value, is going to change.